Somewhere on the floor of the Pacific, 4,000 meters down, a metal chamber closes itself over a patch of mud. No light has touched this place in millions of years. Inside the chamber, oxygen sensors start counting. Scientists expect the number to fall, because that's what always happens when you seal off a patch of seafloor from the world above. Instead, the number climbs. It climbs and climbs, until it's 3 times higher than it should be. Nobody in the room can explain it, because the thing making the oxygen, if anything is making it at all, is sitting in total darkness, half a mile below where sunlight gives out. The question that follows will split the ocean science world in two. Can the deep sea make its own air? For 100 years, the answer to that question seemed settled. You breathe because plants and plankton split water using sunlight, and a fraction of that oxygen eventually sinks into the deep. Down there, in the permanent dark, nothing photosynthesizes, so nothing is supposed to produce oxygen locally. The abyss survives entirely on hand-me-downs, oxygen brewed at the surface and physically dragged down by ocean currents. Think of it like a city with no power plant of its own, kept alive purely by cables running in from somewhere else. Cut the cables, and the lights go out. The cable, in this case, is a slow-motion river bigger than anything on land. The global thermohaline circulation, sometimes called the ocean conveyor belt. Warm surface water flows toward the poles, cools, gets denser, and sinks, dragging fresh oxygen down with it, then crawls back along the bottom of the world over the next 1,000 years. That system depends almost entirely on one narrow gap between 2 continents. Between the southern tip of South America and the edge of Antarctica sits an 800-kilometer strip of open water called the Drake Passage. Roughly 34 million years ago, tectonic plates finally pulled apart far enough to open a true deep water connection there, and everything changed. Once that gateway opened, water could flow all the way around Antarctica, uninterrupted, for the first time in Earth's history. That flow became the Antarctic Circumpolar Current, the single largest current on the planet, carrying somewhere around 135 to 150 sverdrups of water through the passage, which is roughly 135 times the combined flow of every river on Earth. But that current alone doesn't oxygenate the abyss. You need turbulence, real mixing, to force oxygen-rich surface layers down into the deep, because stratified ocean water doesn't want to mix on its own, any more than oil wants to mix with vinegar. The Drake Passage happens to be full of underwater mountains, including a ridge called the Shackleton Fracture Zone, and when the current slams into that terrain, it throws up massive internal waves that break and churn the water violently. Diapygnal mixing in the Drake Passage runs about 20 times stronger than in the open Pacific just to the west, and roughly a fifth of all the wind energy entering the world's oceans gets burned up right there, breaking waves you'll never see from any ship's deck. That churn is what powers the AMOC, the Atlantic half of the conveyor belt, and it's the reason cold water at the poles can sink, drag oxygen with it, and keep the deep sea breathing at all. But here's what should stop you. That system is not as steady as it sounds. Instruments strung across the Atlantic at 26.5 degrees north recorded the AMOC weakening by about half a sverdrup every year between 2004 and 2012, as meltwater from Greenland dilutes the dense, salty water that's supposed to sink. The engine that oxygenates the abyss is already stuttering, which is exactly why the idea of a second, independent oxygen source down there landed like a bombshell. In July 2024, a team led by Andrew Sweetman, working with chemist Franz Geiger, published a study claiming they'd found oxygen being generated right there on the seafloor, in the pitch dark, with no sunlight involved at all. They called it dark oxygen production. The site was the Clarion-Clipperton Zone, a stretch of abyssal plain between Hawaii and Mexico, roughly the size of a small continent, scattered with potato-sized mineral lumps called polymetallic nodules. Those nodules are already the single biggest prize in deep-sea mining, packed with manganese, nickel, cobalt, and lithium. And this is where it gets strange. The researchers proposed that the nodules themselves were acting like natural batteries, generating enough electrical charge on their surfaces, measured at up to 0.95 volts, to split seawater apart into hydrogen and oxygen without any sunlight required. A rock, sitting in the dark, quietly running its own tiny power plant. If true, it would have rewritten how we think oxygen reaches the deep sea, and it would have handed a devastating argument to anyone trying to stop seabed mining, since scraping up the nodules would mean switching off part of the ocean's own oxygen supply. Conservation groups picked it up almost immediately, and the claim reached the International Seabed Authority itself. Astrobiologists got interested too, because if a rock alone can split water into oxygen with no sunlight, that same trick could theoretically be happening right now on Jupiter's moon Europa, or Saturn's moon Enceladus, worlds with oceans buried under ice and no sunlight at all. But that's not the strange part. The strange part is what happened when other scientists actually checked the physics. Splitting seawater into hydrogen and oxygen doesn't just need a little electricity, it needs at least 23 volts under normal surface conditions, and the nodules never measured higher than 0.95. That's not a small shortfall, that's a hard wall, because you can't push a chemical reaction uphill without enough energy to get it there. And down at 4,000 meters, the water pressure is around 400 times what you feel at the surface, which makes the reaction even harder, not easier, since splitting water into gas means those gas molecules have to physically expand against that enormous crushing weight. Critics didn't hedge on this. Some called it a direct violation of the second law of thermodynamics. Then came the part that really unraveled the story. Electrolysis always produces hydrogen gas as a byproduct alongside the oxygen, every single time, with no exceptions. Yet the original study never reported measuring any hydrogen at all. Independent researchers went back through the raw field data and found something even more damning. Some of the exact spots where oxygen spiked, specifically a site called APEI 7, had barely any nodules present in the sediment at all. The oxygen was showing up in places where the rocks supposedly responsible for making it weren't even there. And in a set of test runs where the chamber sealed off, nothing but plain seawater. No sediment, no nodules, no biology of any kind. The oxygen reading still climbed in 2 out of 3 attempts. That's the kind of result that points not to a hidden chemical process, but to something far less exciting. A drifting sensor, a leaking seal, off-gassing from the equipment itself. So here's the loop. Closed. The deep ocean almost certainly isn't manufacturing its own oxygen down there in the dark. The abyss still breathes exactly the way it always has, through a chain that starts with wind screaming across the Southern Ocean, funnels through a gap between 2 continents, and ends 1,000 years later as a trickle of oxygen settling onto the seafloor. It's a system so violent at the surface that it has swallowed entire ships, and so patient in the deep that a single drop of water takes a millennium to complete the trip. And that's what makes this whole episode worth sitting with, because the exciting version of the story, rocks quietly breathing life into the abyss, turned out to be wrong, and the true version is somehow stranger. The reason anything can survive down there at all is a wind pattern circling a frozen continent, doing a job that no one designed it to do. If a handful of scientists can look at the exact same ocean floor and walk away with opposite conclusions, what does that tell you about how much of the deep sea we still haven't actually figured out? 4,000 meters down, in water that hasn't seen light since before there were mountains where your city now stands, the ocean is still, quietly, breathing. It just isn't breathing the way anyone thought, for a few months in 2024, that it might be.